Did the universe truly emerge from nothing? Even asking this question stretches the limits of the human mind, because we are not only talking about the beginning of matter, but of time and space themselves. We are here for those who do not simply look at the sky, but seek to understand it. If you want to take one step closer to understanding the universe, don't forget to like the video and subscribe to the channel. Until the early 20th century, scientists believed the universe was eternal and unchanging. That changed when Albert Einstein united space and time into a single fabric. His theory of general relativity revealed that space and time are not a fixed stage, but a dynamic structure shaped by matter and energy. The universe did not have to be static. It could expand. It could contract. This idea was taken further by the Belgian priest and physicist Georges Lemaitre. Lemaitre proposed that the universe began from an extremely dense and hot state in the distant past. According to him, everything originated from a single concentrated beginning he called the primeval atom. This idea would later become known as the Big Bang. The word bang is misleading. This was not an ordinary explosion occurring in empty space. Space itself began to expand. Galaxies did not scatter into a pre-existing void. The fabric of space itself was stretching. The strongest evidence for this theory arrived in 1965. The cosmic microwave background radiation. This faint radiation, detected uniformly in every direction of the sky, is the thermal remnant of the early universe, emitted roughly 380,000 years after the Big Bang. This light still fills all of space today. It is direct proof that the universe began in a hot and dense state. Today we know the universe is approximately 13.8 billion years old. Over this vast span of time, stars were born, galaxies formed, planets took shape, and on at least one planet, the universe began questioning its own existence. But the most striking fact is this: the Big Bang did not occur within space. Space and time themselves came into existence in that moment. The question, what existed before the beginning, is problematic for this reason. Even the concept of before requires time. Where time does not exist, neither does before. The universe may have emerged from nothing in the way we understand it, or from a physical reality we have yet to comprehend. Quantum fluctuations, vacuum energy, and multiverse scenarios attempt to offer alternative explanations. But one fact remains certain: the universe has a past, and that past is measurable. The universe is not an infinite stage. It has a beginning. There is a moment when time, space, and matter came into existence. And if something has a beginning, it will, without doubt, have an end. In the 1920s, American astronomer Edwin Hubble made a striking discovery while studying distant galaxies. They were not moving toward us. On the contrary, nearly all of them were moving away. Moreover, the farther they were, the faster they receded. This discovery proved conclusively that the universe is not static. Hubble saw this in the light of galaxies. When the light spectrum is examined, the light from receding objects shifts toward the red end of the spectrum. This is called redshift. Light waves stretch, their wavelength increases. This is direct evidence that the source is moving away from us. This observation shows that the universe is expanding, but the real question is, how fast? Today, we call this expansion rate the Hubble constant. Yet there is an intriguing problem. Measurements do not perfectly agree. There is a small but significant difference between data from the early universe and observations of the nearby universe. This tension is one of the greatest challenges in modern cosmology. Then came an even more startling discovery. In 1998, observations of distant supernovae revealed that the expansion was not slowing down. It was accelerating. Despite gravity, the universe had begun expanding faster over time. At this point, the concept of dark energy entered the picture. We do not know exactly what it is. We cannot see it. We cannot measure it directly, but we observe its effects. This mysterious energy, thought to make up about 70% of the universe, appears to be pushing space itself outward. The expansion is no longer simply continuing, it is accelerating. Today, the James Webb Space Telescope is observing galaxies from the early universe to measure the history of this expansion with greater precision. Looking at more distant galaxies means looking back in time, because their light takes billions of years to reach us. Webb is revealing details about the universe's infancy. Now we arrive at the dramatic question: what happens if this acceleration continues forever? Galaxies will drift so far apart that at some point we will no longer be able to see others. The night sky will grow darker. The Milky Way will become the only visible island in the observable universe. A cosmic loneliness will begin. The universe is not merely expanding. It is pulling its own structures away from one another. And if this acceleration is truly an inevitable fate, where will this expansion ultimately lead us? The stars that illuminate the universe will not burn forever. They are powerful on a cosmic scale, but they are not immortal. Everything begins with vast molecular clouds of gas. Gravity slowly pulls these clouds inward, compressing them. Temperature rises, pressure increases. At a critical point, nuclear fusion ignites. Hydrogen atoms fuse into helium. Energy is released. A star is born. Stars live and die according to their mass. Our star, the Sun, has been burning for about 4.6 billion years. It has roughly 5 billion years of fuel remaining. When the hydrogen in its core is exhausted, its balance will collapse. It will expand into a red giant. It is highly likely to engulf the inner planets. By that stage, Earth will have long since lost its habitability. More massive stars meet far more dramatic ends. They consume their fuel rapidly. Their cores collapse. Then, in a colossal explosion, they eject their outer layers into space. A supernova. A supernova is not merely a death. It is also a production site. Heavy elements such as iron, gold, and uranium are forged in these explosions. Some of the atoms in the human body were created in a supernova that occurred billions of years ago. In some cases, the remaining core is so dense that not even light can escape. A black hole is born. Black holes are often imagined as eternal structures of darkness. But in the 20th century, physicist Stephen Hawking proposed a striking idea. Due to quantum effects, black holes are not completely black. They emit radiation extremely slowly. This process is known as Hawking radiation. This means black holes are not permanent. Given enough time, they evaporate. Now let us make a leap forward in time. 1 billion years from now, the sun will be brighter. Earth's oceans may have largely evaporated. Life will become severely strained. Now move ahead 1 trillion years. The formation of new stars will nearly cease. The gas reservoirs within galaxies will be depleted. The universe will have long passed its brightest era. The sky will grow darker. Stars will extinguish one by one. Energy disperses. Order declines. Sources of light become rare. The universe will still exist, but it will be quieter, colder, emptier. The birth of stars brought brilliance to the cosmos. Their deaths left behind heavy elements and black holes. But star formation will not continue indefinitely. As light sources diminish, cosmic isolation will deepen. This is not a declaration of an ending. It is the era in which energy slowly begins to withdraw from the stage. As the universe continues to expand, galaxies will begin to drift beyond one another. This separation will not occur as an explosion or a sudden rupture. It will be a silent, gradual, but irreversible process. As the distances between galaxies grow, their light will eventually become unable to reach us. This is where the concept of the cosmic horizon comes into play. The cosmic horizon defines regions of the universe that no longer have a causal connection with us. No information, no light, no influence from those regions will ever reach us. For us, they do not disappear physically, but temporally. As time passes, this horizon does not shrink, it expands. The observable universe becomes smaller. More galaxies cross beyond the cosmic horizon. The universe still exists, but the portion accessible to us steadily diminishes. Meanwhile, matter density decreases. Galaxies grow more sparse. Energy spreads across larger volumes. The universe evolves toward a structure that is emptier, colder, and more disordered. The universe may become a more empty place over time, more isolated, more tranquil. But this is not a narrative of annihilation. It is the narrative of change itself. Time moves forward, the universe transforms, and we exist within a brief cosmic moment as beings attempting to understand that transformation. Perhaps the real question is not what the distant future of the universe will be. Perhaps the real question is, in this short moment, how much of the universe have we truly understood?